Hello students, having discussed the infinitely long fin case where I had given the formula for the temperature distribution and also for the heat transfer rate through the fin. Now I will consider the more important case of the fin called as the insulated tip fin case. Almost in every fin problem by default, whether if sometimes he mentions, if he doesn't mention any case, by default we will consider that insulated tip fin case. Okay. Now let me indicate that insulated tip fin case like this pictorially. Case 2, this is also famously known as case 2 among the three fin cases. Fin is finite in length. Fin is finite in length. It is not infinitely long, but its tip is insulated. It is like this. Fin is finite in length, but this tip is insulated. A is the profile area of the fin, T naught is the base temperature. Okay. Because the fin's tip is insulated, there cannot be any convection heat transfer from the tip. Q convection from tip is equal to 0. T naught is the root temperature or the base temperature. This is the x direction. Okay. Now, earlier I had given the equation, temperature distribution, equation for temperature distribution T minus T infinity is equal to C1 into e to the power of minus mx plus C2 into e to the power of mx, right? Where m is equal to root of hb by k. One boundary condition we have already seen here. At x is equal to 0, temperature is T naught. The other boundary condition is obtained from this particular given condition that tip is insulated. Because the tip is insulated, there cannot be any convection from the tip. When there is no convection heat transfer from the tip, the heat conducted into the tip must be equal to the 0. Heat conducted into the tip should be equal to 0. That is the second boundary condition. Heat conducted when heat conducted into the tip is equal to 0 minus Ka at x is equal to L is 0. K cannot be 0, A cannot be 0. Therefore, dt by dx at x is equal to L is equal to 0 implies d theta by dx at x is equal to L also will be equal to the 0. So, this is the second boundary condition. I can say this is the second boundary condition for obtaining C1, C2. This is the second boundary condition. One boundary condition you are getting from the figure. At x is equal to 0, t is equal to t naught. So, that is one boundary condition. This is the second boundary condition. From these two boundary conditions, we can obtain the two constants of integration C1 and C2. Once we obtain the C1 and C2, we know the temperature as a function of x. M is root of hp by Ka. We already know that M is given by root of hp by Ka. So, once we get the C1 and C2, that means the temperature becomes a function of x. We know that function as a becomes a function of x. That function I am giving here. Then the temperature distribution within the fin For case 2, for insulated tip case, most of the fin problems we assume this particular case. For insulated tip case is T minus T infinity by T naught minus T infinity is equal to cos H m L minus x by cos HML. This is an hyperbolic cosine. Cos h means this is a hyperbolic cosine. M is root of HB by Ka. From this particular temperature distribution, we can calculate the temperature of the fin at an Ex. At an Ex, we can calculate the temperature of the fin. T infinity is the ambient fluid temperature. This is the first objective. In every fin problem, we are dealing with two objectives. One is temperature distribution within the fin. Second thing is heat transfer rate through the fin. So, heat transfer rate through the fin. Second objective is heat transfer rate through the fin. I have given you yesterday already earlier class. I had given what is the general rule for calculating the heat transfer rate through the fin? Q conducted into fin. Q conducted into fin at x is equal to 0. That is at x is equal to 0. That is minus Ka dt by dx at x is equal to 0. The heat conducted into the fin at the root of the fin, at the root here, this is whatever the heat conducted here at the root of the fin is the total heat transfer rate from the entire fin. So then that would result in, this is the final formula, square root of Hp Ka T naught minus T infinity into tan HML. This is the formula we need to remember. This is the temperature distribution. This is the heat transfer rate through the fin. Always remember these two formula. Most of the fin problems we may have to use this case. Okay. If no case is, remember, if no case is mentioned in any fin problem, by default assume case 2 in any gate problem also. If no case is mentioned, by default assume case 2. I am writing that note also. If no case mentioned in any fin problem, assume case 2, right. Now I will do the next case, case 3. This is a general case. This is a very general case. Fin is finite in length, but its tip is not insulated. Fin is finite in length, but its tip is not insulated, uninsulated tip. That means there is a convection heat loss from the tip also. That is, there is convection heat loss from the tip also. That point is there. There is a convection heat loss from the tip also. Finite in length. A is the profile area of the fin, tip not insulated. Q convection from tip also. It is a general case of fin. Finite in length, there is a convection heat loss from the tip also. The solution for this case and the solution for the case are exactly the same, but only with slight difference that the length in the L, in the solutions, the L in the insulated tip case you have to replace with L by LC, corrected length. L by 2 for the rectangular fin, L is equal to D by 4 for the pin fin. Okay, I mean to say that whatever the formula we have given for the insulated tip case, we can use it for this case also, but with slight correction that the L in the formula we have to replace with the LC, corrected length. That LC is given by D by 4, where D is the diameter of the pin fin, diameter of, this is a pin fin. If it is a rectangular fin, LC will be corrected length will be L by 2. I am writing here the same formula, the solution for temperature distribution for this case also is given by T minus T infinity divided by non-dimensional formula I am giving, T naught minus T infinity is equal to cos Hm, instead of L we have to write LC, cos Hm LC minus X by cos HMLC, where LC is equal to corrected length. Which is given by L by 2 for rectangular fin, LC is given by, I am writing here, L by 2 for rectangular fin, sorry, T by 2, LC is given by T by 2 L plus T by 2 for rectangular fin slight extra length we are providing. Are you able to get? I am writing more clearly here. LC is given by that corrected length is given by LC is equal to L plus T by 2, where T is the thickness. LC is equal to L plus D by 4 for rectangular fin. Please note that what I mean to say here is, whatever the formula we have put up for the case 2, we can write for the same formula for the case 3 also. What is the case 3? There is a Q convection from tip also, but same formula, but with slight error, slight correction in the length. Instead of L in the case 2 formula, we have to write LC. What is LC? LC is equal to L plus T by 2 for rectangular fin. LC is equal to L plus D by 4 for sorry, it is not rectangular fin, for pin fin. Pin fin means circular, like this, circular cross section for pin fin. Then heat transfer rate through the fin also the same formula as that of the case 2, but only with correction. L is replaced with LC. Square root of HPKA T naught minus T infinity into tan HMLC. Please note that case 2 formula and case 3 formula are exactly the same. Only thing is the L in case 2, now here we have replaced with the LC. LC is given by L plus D by 2 for rectangular, LC is given by L plus D by 4 for the pin fin. But for that there is no difference. That means if no case is mentioned in any fin problem, by default take the case 2. You consider this case only when he specifically mentions in the problem that there is convection heat loss from the tip also. Otherwise, we can take almost a second case. Almost in every problem of the fins, we always consider second case. Okay. Now, having done the fin problem, fin analysis for all kinds of the cases, now I will define two important parameters. Performance of the fins can be evaluated by two important dimensionless terms called as fin efficiency and fin effectiveness. First, let me define fin efficiency. It is defined as the ratio between heat transfer rate through fin, actual heat transfer rate through the fin, and the maximum possible heat transfer rate through the fin, heat transfer rate through the fin that is when the entire fin surface is at its root temperature. Root or base temperature. That is when the entire fin surface is at its root or base temperature. It could be understood like this. This is a definition of the fin efficiency, defined as the ratio between actual heat transfer rate through the fin and the maximum possible heat transfer rate through the fin that can occur through the fin. That is when the entire fin is at its root or base temperature. It can be understood like this. Now, actually there is a heat transfer rate is happening from the fin. I'm assuming that tip is insulated. What is the actual heat transfer rate taking place? Actual heat transfer rate taking place will be square root of HPKA T naught minus T infinity into tan HML. Okay. L is the length of the fin. Okay. This is actually taking place, in which definitely we notice that the temperature of the fin will drop from the tip of the fin, from the root of the fin up to the tip. The temperature of the fin keeps decreasing from the root to the tip. We all know that though it is made up of the good conducting material, the temperature of the fin keeps decreasing from the root to the tip. Okay. This is actually taking place. What will be the maximum possible that can occur? The maximum possible that can occur is, that is when the entire fin surface must be at the same base temperature or the root temperature. When that can happen? When the entire fin will be at the root or the base temperature, the whole of the fin will be at the base temperature only when the material of the fin has got infinite thermal conductivity. If the material of the fin has got infinite thermal conductivity, there would not be any thermal resistance offered by the fin material. Therefore, there will not be any temperature drop. The whole of the fin will be at the same temperature T0. In case only when the material of the fin is having the infinite thermal conductivity, that is, the fin material is not offering any conduction thermal resistance. So, under that only, that there will not be any temperature drop. So, that I will calculate that maximum possible also. Same fin, now it is at material is having, same fin, now the material is having infinite thermal conductivity, tip is insulated, the whole of the fin is at the base temperature T0, the whole of the fin. And every location of the fin is at T0. Then what will be the maximum possible heat transfer rate? The whole of the fin, what is at the base temperature? Then what is the convection area? P. P is the perimeter. If D is the diameter, what is the perimeter of the fin? Pi D. P is the perimeter of the fin, pi D. The total convection area will be, perimeter into length of the fin. That is actually happening. This is the maximum possible. Maximum possible will be, you can observe, only when the material of the fin has got infinite thermal conductivity, that is, this fin material is not offering any conduction resistance. Therefore, the formula for the fin efficiency will be, for the insulated tip case, Q actual will be maximum possible will be so this will result in, efficiency of the fin will be tan HML by ML. Please remember this formula for insulated tip case. This formula holds good for case 2. For the insulated tip case, this formula will tan HML by ML. Remember this formula for the insulated tip case. This is the efficiency formula. Then you may ask, then what is the fin efficiency formula for the infinitely long fin will be? For infinite efficiency of the fin will be 1 upon ml for very long fin. Case 1, for very long fin, this is a formula. If it is a case 3, is very simple. All the formula for the case 2, we can use it for case 3. Only thing is, instead of L, we have to write the LC. That is the only difference. Whatever the formula you are writing for the 2, we can simply write it for the 3 also. Only difference is the formula in L we have to replace with the LC. That is the only thing. Now that means for the case 3, what is the fin efficiency formula? Tan HMLC by MLC. For case 3, supposing if you want to write the case 3, tan HMLC by M into LC for case 3. Case 3 means what? Case 3 means uninsulated tip. This is for case 2. This is for the case 2. Insulated tip case. This question was once asked in GATE also, recent GATE. So, fin efficiency, we should understand what is actually happening from the fin divided by what could be the maximum possible that could happen from the fin. That is when the entire fin should be at the base temperature T0. That is when the material of the fin has got infinite thermal conductivity. Now, I will define the second performance parameter called as the fin effectiveness. Fin effectiveness epsilon. It is defined as the ratio between heat transfer rate with fin and the heat transfer rate without fin. Heat transfer rate with fin and the heat transfer rate without fin. That is the definition of the fin effectiveness. Now, you can understand this formula like this. You can understand the definition of the effectiveness of the fin like this. Suppose that there is a finite length of the fin is there with the insulated tip case. Most of the formula I am deriving for the insulated tip case because almost all the fin problems we do it assuming the case 2. So, L is the length of the fin and T0 is the root temperature. A is the profile area. A is the profile area. Cross-sectional area also called as the profile area. Now, what is the heat transfer rate from the fin? Heat transfer rate from the fin will be square root of HPKA T0 minus T infinity into tan HML. So, this is the with fin actually. Now, what I have done is I just cut off the fin and remove. I just cut off the fin and removed. The fin was removed. Now there is no fin as such. Now it is a bare wall. Okay. From the bare wall, now without the fin, now we have the wall with the without fin. Now from the same profile area, now there is a fin. Now there is no fin. Without fin, how much heat transfer rate will be taking place from the same area A? How much heat transfer rate will be taking place after removing the fin? We have certain base area, from the fin. From that base area located on the wall itself, from that this base area, this is the base area. From the same base area, how much heat would be transferred directly from the base wall to the fluid? If this is T0, if this is T infinity, Q without fin will be HA T naught minus T infinity. Q without fin, no fin now. The ratio between them is it is understood as fin effectiveness of fin, with fin divided by without fin. So for the insulated tip case, I will derive the formula, because with fin and without fin we already know it. With fin and without fin we already know it. With fin, heat transfer rate with fin through fin will be divided by, so these two will get cancelled. Square root of HEA by Kp. A is the profile area. This is the formula for the effectiveness of the fin. What is the physical significance, physical meaning of physical significance of this effectiveness of the fin? Effectiveness of the fin, if you just look at the definition point of view, effectiveness of fin tells about by keeping the fin, how much percentage increase in heat transfer rate we are able to achieve. I mean to say, whether the fins are really helping us or not. That means how much help, how much percentage increase in heat transfer rate we are able to observe by keeping the fin as compared to the case where there is no fin. That is given by this effectiveness. Effectiveness of the fin is telling about whether the fins are really helping us or not. Are the fins useful or not? Whether the fins are helping us or not. That particular answer can be given by seeing this formula, by seeing this definition called effectiveness. If the effectiveness of the fin is very high, I mean to say that yes, I can say that fins are really helping us in increasing the heat transfer rate. On the other hand, if the effectiveness of the fin is low, supposing effectiveness of the fin is say 1.1, say for example, 1.1, say for example. Do you think that fins are really helping us then? If the effectiveness of the fin, I say for example, it is 1.1, then what is the percentage increase in heat transfer rate by keeping the fin? 10%. So I can say that I can judge that yes, it is a waste of keeping the fins. If you want to say that fins are really helping us by keeping the fins, heat transfer rate at least must increase by double. Minimum it should get doubled heat transfer rate as compared to the without fin. After keeping the fins, heat transfer rate must definitely should get doubled. Then only I can say that fins are worth keeping, fins are really helping us. If there is a meager 5% increase or 10% increase in heat transfer rate after keeping the fin, I can say that don't keep the fins. You run the show without the fins, because fins are money, fins are material, fins are extra design, extra component you are putting in. After spending so much of effort, so much of money, material, if you attach the fin, if you just get 5% or 10% increase in heat transfer rate, it is not worth keeping the fins. Don't keep the fins. You just run the show without the fins. So I can say by looking at the effectiveness value, you can judge, you can decide whether we can go for the fins or just run the show without fins. Just don't keep the fins. That decision. So that decision of whether you have to keep the fins or not to keep the fins, just run the show as without fins. So that decision is taken by the value of the effectiveness. That is the physical meaning of the effectiveness. I hope I understood that. If you want to keep the fins, if you want to keep the fins, the minimum value of the effectiveness should be 2. If the effectiveness is 4, yes, I can say that fins are really helping us in increasing the heat transfer rate. If the effectiveness is say 1.1, don't keep the fins, just on, because fins are material, fins are money. We are investing something, but the return is only 5% increase or 10% increase. It is a waste of keeping the fins. So that is the physical significance of the effectiveness of the fin. I can write that effectiveness of fin tells about how much percentage increase in heat transfer rate we are getting after keeping the fins as compared to the case where there is no fin. As compared to the case where there is no fin. We keep fins only if effectiveness of the fin is greater than 2. Okay. So fins are worth keeping only if effectiveness of fin is high enough. We can see in the previous formula also, we can observe that effectiveness of the fin is directly proportional to the 1 by root h, is directly proportional to the root of p by a. Okay, there are certain things we can understand from this formula. Effectiveness of the fin is directly proportional to the 1 by root h. That means if the h value is high, effectiveness is low. This is the reason why we do not keep the fins. We do not keep the fins with water, because with water h value is quite higher. On the other hand, if h is low, effectiveness of the fin will be higher. When the h value is low, that is with gases, that is with air. So this is the reason why fins are always used with gases, are always used only when gases are coolant. Since h value is low. Since h value is low with gases. With air, what is the h value? Around 15-20 watt per meter square Kelvin. On the other hand, with water, h value, minimum value of h will be around 600 or 700 or 1000. So with water, the h value being very high, effectiveness will be low. So whether you keep fin or don't keep fin doesn't matter, not much difference. That is why wherever you see the fluid around the fin, by default it will be a gas, it will be atmospheric air. Okay, this is the reason. Effectiveness of the fin is also directly proportional to the P by A. P is the perimeter, A is the profile area. This ratio will be high if the thickness of the fin is low. This is the reason why fin is always made thin. The thickness T dimension will be few mm, 2 mm or 1 mm or 3 mm. Therefore, you can say, to have high effectiveness of fin, this question was once asked in GATE. To have high effectiveness of fin, fins must be thin and closely spaced fins. Fins must be thin like this. This is a usual configuration of the fin we observe. In fact, best example is car radiator. Best example to understand the fins is car radiator. A good number of fins, thin fins, closely spaced fins. Like best example is radiator, car radiator. On the car radiator, we see the thin fins, very thin fins like this. Thickness will be around a few mm, very thin fins. Thin and closely spaced fins like this. Not very close, there must be some gap must be left to allow for the flow of air. Air must go in between, but they will be closely kept so that a number of fins can be accommodated. And effectiveness of the fin is directly proportional to the root k, and incidentally efficiency of the fin is also directly proportional to the k. Therefore, fin must be made up of good thermal conductivity material. Therefore, fin material must have high thermal conductivity. Must have high thermal conductivity. The thermal conductivity of the fin material must be high. Best example for the fin is aluminum. Aluminum is the best material for the fin, and copper also, sometimes copper also we can use. They are the best materials for the fin. Fin material must have the high thermal conductivity like aluminum, or copper is heavy. Copper is costly also. Aluminum I give the more marks. Light material and cheap also, good thermal conductivity. So, whenever we are designing the fin, a fin design must be thin and closely spaced fins, a number of fins, good number of fins. Whenever we are keeping the fins, we do not see 5 fins or 10 fins, we always keep around 50-60 fins. Even if you electronic devices also, if you see, there will be a thin fins will be there, small length fins. They are usually soldered. They are soldered to the electronic devices because they also need cooling. When you are attaching fins to the electronic devices, usually they are soldered, a small length projection. So, I can say that fin must be not very long, moderately short. Long fin is economically not correct. Moderately short fins, thin fins, closely spaced fins, a good number of fins made up of a high thermal conductivity material like aluminum or copper. That is a correct design for keeping the fins. That they are the correct design features. Okay. Look at this. The insulated tip temperature of a rectangular fin having an excess root temperature theta naught is. Okay. The insulated tip temperature of a rectangular longitudinal fin have over ambient root temperature theta naught is. That means T minus like he is asking about this particular, the insulated tip case 2, that means he is asking the case 2 insulated tip case. This he is asking here. Here what is theta? He is asking theta by theta naught is equal to T minus T naught by, he is asking about theta having a root temperature. This is T naught, this is the ambient temperature. Cos h m L minus x divided by cos HML, where we have to put x is equal to L, because he is asking at x is equal to L. This is the x direction. When you put x is equal to L, here L minus L 0, cos HML will be 1, that is it becomes 1 by cos HML. Therefore, theta is equal to theta naught by cos HML. Answer is D. He is asking what is theta value here. Here x is equal to L, right? X is equal to 0 here. Here x is equal to L. What is theta? Insulated tip temperature of rectangular fin. He has asked the rectangular fin, but whether you do it for the pin fin also, answer will be the same. It doesn't have to mention rectangular. Even if it is a pin fin also, answer will be the same, doesn't matter. Though he has mentioned rectangular, same answer we can adopt for the pin fin also. Okay. 3 fins of equal length and diameter made up of aluminum, brass and cast iron. At one end, there are 3 fins of the same length, okay, equal length. One end is a T naught is 200 degrees Celsius, ambient is 25 degrees Celsius. The temperature at the free end, you know that in all the 3 cases, temperature will drop. One material it may drop like this, another material may drop like this, and another material may drop like this. Now, if you just see the 3 colors indicating 3 materials, which material is for which color means a material having more thermal conductivity. I can say that if the material of the fin has got more conductivity, the temperature drop between the base and the tip will be lesser. More the conductivity of the material, I can say, more the conductivity of material, thermal conductivity. More the thermal conductivity of material of fin, lesser will be the temperature drop. Lesser will be temperature drop from the root to the tip. Lesser will be temperature drop from the root to the tip. Okay, from that I can easily say that this color, this color will be which has got the more this is for the aluminum. Second thing is for brass is an alloy of copper. This is the cast iron. Cast iron has got conductivity only 50. Brass has got around 250 or 300 like that. Brass is this one. This is brass. Brass is more conducting than aluminum. K of the brass. Brass is an alloy of copper. Brass is alloy of copper. Brass, bronze, they are all the alloy of copper. Therefore, they will be having more thermal conductivity than aluminum. Pure copper has got a conductivity of around 390. Aluminum has got a conductivity of 200. Cast iron has got a conductivity of 50 watt per meter Kelvin. You can have a rough idea about which has got more, which has got lesser. So, this is a very good question regarding the fins only. This question also. 2 rods, one of length L and other of length 2L are made up of the same material and having the same diameter. Both the ends of the rod are maintained at 100 degrees Celsius. two rods, one of length L and other of the length is 2L. First I draw it. Okay. This is 100 degrees Celsius. This is also 100 degrees Celsius. Length is 2L. Okay. Ambient is 20, around 40. Now we have a single rod of length L only, not 2L, of length L. But this tip is insulated. This tip insulated. It's a very good question, asked in GATE and engineering services also. This same question was asked in GATE and as well as the engineering services also. And both are exposed to the same, they both are having the same root temperature. Both are having the T0, no? T0, both are having the same temperature, 100 degrees Celsius. Temperature at the insulated tip, he has mentioned, no? This is insulated tip. This temperature is given as 55. Then what is the temperature at this midsection? At the midsection of the longer rod, what is the temperature is asking. To answer this question, one should have a complete idea about boundary conditions of the fins. For all the cases of fins, we should have the boundary conditions. Like this is the midsection. That means this length is L. This is the midsection, this length is L. So from the symmetry of this figure, so at this, from the symmetry at the midsection, the temperature profile, if you see, it will be like this. If you join, see, what is the dt by dx here? At this location, dt by dx is equal to 0. At that location, dt by dx is 0. Now here also the dt by dx is 0 at the midsection because the temperature is minimum there. At this location also, dt by dx will be 0. So, here also dt by dx 0. Now, whatever the temperature, see, this is T0, right? This is T0. This is also T0, you can consider. Now, if we just take two rods of the same length, same diameter, same base temperature, if we just attach the end to end two rods are there like this, same length of the rods, same diameter, same root temperature, and both are attached here end to end, there cannot be any conduction here because these at this section and at this section temperatures are same. If we just take two rods, root temperatures are same, ambient temperature is same material, same diameter, same length. If you just attach like this, there cannot be conduction between these two locations here. Why there cannot be any conduction? Because their temperatures are same. How can there be conduction? There cannot be any conduction. When there cannot be any conduction, obviously that dt by dx will be 0. Since no conduction here. Here no conduction along x. No conduction along x. Why no conduction along x? Because temperatures are there same. When no conduction along x, minus Ka dt by dx is 0, therefore dt by dx is 0. So this boundary condition and that boundary conditions are same. That here the root temperatures are also same. So whatever the temperature you see here, same temperature you see here. Here the temperature is 55. Answer is C. We should understand that why dt by dx is 0 here, because this is insulated. When it is insulated means Q conducted is 0. Look at the second boundary condition of the case 2. So, here at 100 degrees Celsius, here 100 degrees Celsius. Here dt by dx is 0, here also dt by dx is 0. Same length, same diameter, same material, made up of the same material, everything is same. So, whatever the temperature you see here, 55, same temperature you will see at the midsection also. This is an excellent problem given in both GATE and as well as Indian Engineering Services prelims examination. So, such kind of a questions you should clearly understand, particularly as regard to the boundary conditions. How I can say that temperature is 55 here? Because boundary conditions are same. Here 100, here also 100. Here the dt by dx is 0. Why dt by dx is 0? Because no conduction along x here. Why there is no conduction? Because temperatures are, so it is like this. Supposing if you take two rods, two rods, same length, same material, same temperature here and here. Now the here and here also the temperature T is same. When you join both of them, supposing if this is L, if this is L, if you join both of them, you will get this. Both the locations, same diameter, same material, same root temperatures, same length here also. Obviously, when the ends are joined, there can no conduction possible because temperature is same. No conduction possible means dt by dx is 0. Looking at the boundary conditions, I can say the temperature is 55 here also because that is given 55. So, this is the variable thermal conductivity. Generally, this question, if the thermal conductivity of a material may be a function of temperature. In all the earlier cases, conductivity we have assumed as a constant. Some cases, conductivity may become a function of temperature. It can be K naught into 1 plus or minus alpha T. Okay, alpha is some constant there. K may be, in such case, if you just look at the one-dimensional conduction through a slab, one-dimensional conduction through a slab, if you consider if this is x direction, we know that if K is constant, temperature drops linearly. If K is constant, temperature drops linearly. In case if the K is a variable conductivity like that, this curve is for the K naught into 1 plus alpha T. K naught into 1 plus alpha T. This curve will be K naught into 1 minus alpha T. This will be the K is equal to constant. If you just T1 is greater than T2. So, see that the temperature at the center of the wall, this is the center, right? This is the center of the wall. At the center of the wall, when the K naught into 1 plus alpha T, in case of the constant thermal conductivity here, see this, as compared to constant thermal conductivity, in case of the K naught into 1 plus alpha T, the temperature will be more. Answer is A. A is the answer. You can easily see. This is the temperature profile for the K naught into 1 plus alpha. It is a variable thermal conductivity. It is called variable thermal conductivity. When K is equal to K naught into 1 plus alpha T, you will feel more temperature as compared to the case where it is a constant thermal conductivity. A large concrete slab 1 meter thick has one-dimensional temperature distribution. If the slab x is the distance of the one phase, one-dimensional conduction temperature is only a function of x. Okay. If the slab material has got thermal diffusivity alpha, what is the rate of change of temperature at the other face? Other face means at the other, here, this is the 1 meter thick. Here at this location is asking dou T by dou tau. What is that? One dimensional conduction, no? We can write from generalized conduction equation, this is the generalized heat conduction equation, wherein there is not any mention of the heat generation. This Q dot will be there only when there is a heat generation. 1 by alpha into dou T by dou tau. All these terms are 0 because he did not mention anything about the heat generation. So, you will get dou T by dou tau is equal to alpha into dou square T by dou x square. Differentiate that function twice. If you differentiate once, you will get minus 10 plus 40x plus 30x square. Okay, 30 if you differentiate once. So, if you differentiate twice, this will vanish. 40x will become 40 and 30x square will become 30x square, 60, it becomes 60x. 60x plus 40, x is 1, that is 100, that will become 100, yet x is equal to 1 meter if you want, because if you want at x is equal to 1 meter, that is this is equal to alpha into t into 10 power minus 3 into 100, that becomes 0.2 degrees Celsius per hour. This is the rate of change of temperature. What is the dou T by dou tau? Rate of change of temperature with respect to time. With respect to time. Tau is the time here. Mind that this tau symbol I am writing for the time. Tau symbol I always write it for the time. Hello students, having completed the fins, I would like to solve some of the important problems in regarding the fins and as well as the heat generation inside a cylinder. Before the fins, I have covered the heat generation inside a cylindrical body, conduction heat transfer with heat generation inside a cylindrical body. Okay, so regarding these two topics, I will do some important problems which are given like this. Look at this, a cylindrical uranium fuel rod of radius 5 mm in nuclear power plant. Actually, this should be given as nuclear power plant. Nuclear power plant, please add that word here, is generating heat at the rate of 4 into 10 power 7 watt per meter cube. Okay. There is a heat generation inside a cylindrical rod, nuclear fuel rod of how much? Q dot is equal to 4 into 10 power 7 watt per meter cube. Please remember that Q dot symbol is always the symbol used meant for heat generation per unit volume. The rod is cooled by a liquid coolant. There is a coolant here. The rod is being cooled at the surface by a liquid coolant at the temperature of 25 degrees Celsius. Whenever there is a convection heat transfer between the rod and the fluid, the convection mode of heat transfer is always indicated by the convection heat transfer coefficient. Okay, that H value was given 1000 watt per meter square Kelvin. Okay. So, he has asked to calculate what is the surface temperature of the rod, TW. What is that? TW. I already said many times, whenever there is heat generation in any body, whether it is a slab or a cylinder or a sphere, Whenever there is a uniform heat generation inside any body, if you want to calculate the surface temperature of the body, write the energy balance for steady state. What is that energy balance? The total heat generated in the entire rod should be equal to the heat convected from the surface of the rod to the fluid. Okay, that is the most important energy balance equation for steady state. For steady state of rod, heat generated in entire rod is equal to heat convected from the surface of rod to fluid. This is the energy balance for steady state. What is the heat generated? Q dot into volume. Q dot is always the heat generated per unit volume. Q dot into what is the volume of the rod? Pi r square L. So this gives watt per meter cube into meter cube. So this will get cancelled. You will get the resultant will be watts. That should be equal to the heat convected. What is the convection heat transfer area? If R is the radius of the rod, pi r square, that is a convection area will be 2 pi r into L. If L is the length of the rod, okay, 2 pi r into L. Convection area means contact area between the body and the fluid as given by the Newton's law of cooling. Convection area is 2 pi RL, that is the convection area or the contact area. Look at that, perimeter into length of the rod, that is the convection area. What is the temperature difference? HA delta T. A means area of convection, area of contact, from which you can cancel some of the parameters. Okay, L also gets cancelled. You can calculate surface temperature of the rod in degrees Celsius. But please note that after obtaining the temperature in degrees Celsius, he has asked the answer in Kelvin. Okay, you will get the answer in Celsius here. We have to add the 273 to write the answer in Kelvin. That is the problem with the very important precaution regarding the gate. The answer you may be getting correct, but this is a numerical data. You have to type the answer. Okay, so though you got the correct answer, if you don't maintain the proper units in which the answer is asked, you will go wrong. So the answer you will be getting in Celsius because you are substituting T infinity as 25 degrees Celsius. This answer also will be in Celsius. So add 273 to get the answer in Kelvin. So this is a previous gate question recently asked. So the energy balance you have to keep in mind for steady state whenever there is a heat generation. Look at that, heat is generated uniformly in a long cylindrical rod at the rate of thermal conductivity of the rod material given. Temperature difference between the center and the surface of the rod. Yes. We know that whenever there is a uniform heat generation inside the rod, we know that the temperature distribution inside the rod at any given cross section, it will be parabolic with the maximum temperature at the axis and the minimum temperature at the surface of the rod. Whenever there is a uniform heat generation inside a rod, this is the temperature distribution. What is the distribution? Temperature distribution parabolic. This is the parabolic temperature distribution. Where R is the radius. If you just take the T naught minus TW, temperature difference between the axis and the surface will be Q dot R square by 4K, where K is the thermal conductivity. T naught is the maximum temperature at the, that is at axis of rod. Okay, Q dot is given already. What is the Q dot? 4 into 10 power 7 watt per meter cube. Always maintain the proper units. What is the diameter is radius? Diameter is 10, radius will be 5. 5 divided by 1000 whole square divided by 4 into thermal conductivity is 20. You will get the T naught minus TW. T naught is the axis temperature. This is the axis temperature. That is at the axis of the rod. Maximum temperature at the axis, minimum temperature at the surface of the rod. This is also recently asked gate question. So, if it is a sphere, T naught minus TW will be the Q dot R square by 6K. If it is a spherical body, wherever there is a uniform heat generation, if there is a uniform heat generation inside a spherical body, the temperature difference between the center and the surface will be Q dot R square by 6K. Look at this. Which one of the following configurations has the highest fin effectiveness? We already given fin effectiveness will be tan HML by root of HA by KP. Effectiveness of the fin. They already said effectiveness of the fin is directly proportional to the root of P by A, where P is the perimeter and A is the profile area, cross-sectional area or the profile area. If this is the fin, this is the cross-sectional area or the profile area of the fin. In case of the pin fin, that A will be pi by 4d square. So, to have the more effectiveness of the fin, it should be thin fin and closely spaced fin like this. I already given this information earlier also. Fins must be thin, very thin fins we always design, and closely spaced fins. Why closely spaced? To accommodate a good number of fins. Like generally, whenever you are keeping around 50 fins, 40 fins, that number will be like this. To accommodate the large number of fins, the fins must be closely spaced and thin fins. This thickness of the fin is too small. Thin fins and closely spaced fins. Okay, answer is A, to have the high effectiveness. The heat loss from a fin is 6 watts. Actual heat transfer is 6 watts. The effectiveness of the fin is 3 and the efficiency is 0.75. The heat loss from the fin keeping the entire fin surface at the base temperature. So, this problem should be solved by you making use of the efficiency formula of the fin. Efficiency of the fin is Q actual divided by Q maximum possible. When this will maximum possible heat transfer can happen, that is when the entire fin surface is at T naught. This is given as 0.75, right? So, he has given the Q actual. So, he is asking when the entire fin surface is at T naught. What is the T naught? T naught is the base temperature or the root temperature. T naught is the base temperature or the root temperature. Therefore, Q maximum possible is asking. Q maximum possible will be Q actual is 6 divided by 0.75, 8 watts. This is the answer. Effectiveness of the fin is only a superfluous data. He has given that. This is also recently asked a gate question. Okay. In fin problems, in fin chapter, we come across 2 performance parameters. One is effectiveness, another is efficiency. Effectiveness of the fin means what is heat transfer with fin divided by heat transfer without fin. Effectiveness of the fin tells about whether we have to go for the fins or not to go for the fins by seeing the value. Look at the effectiveness value 3 given. That means this fin is really helping us. Any value of effectiveness more than 2, you can go for keeping the fins. If the effectiveness of the fin is less than 2, then generally we do not want to waste our money by keeping the fins. We don't keep the fins. If the effectiveness is say 1.1 or 1.2, we would not go for the fins. We will just run the show without fins. Okay, right. So, they have done the very important problems of fin problems and the heat generation. Now, let me start a new topic in the conduction chapter, very important topic called as the unsteady state conduction or transient heat conduction. Unsteady state or transient heat conduction. What do you mean by unsteady state? In all the earlier cases, in all the including fins, heat generation, etc., composite slab, composite cylinders, etc., we have made one most common assumption that temperature at a particular location within the body do not change with respect to the time. In all the earlier cases I have considered, temperature is not a function of time. Temperature is only a function of location. Maybe temperature is a function of x, temperature is a function of r, like that. That means at a particular location, temperature must not change with respect to time. That is called steady state. Our body is the best example for the steady state. Okay, your human body is at 37 degrees Celsius at any instant of time. If you measure the temperature, it is the steady state. Now that assumption is deleted, removed. Now things are becoming, things are allowed to change with time. Temperature is a function of time. That is the meaning of unsteady state or transient. So this could be understood with this example, a practical example. Suppose that I have taken a body of mass m, volume v, density rho, specific heat Cp, a finite sized metallic body, having the mass m, volume v, density rho, specific heat Cp, is placed inside some metallurgical furnace. A metallic body is kept inside a metallurgical furnace and heated to a sufficiently high temperature in that furnace. Suddenly that body is taken out of the furnace and exposed to the, kept exposed to the ambient fluid, maybe atmospheric air, or that body is dropped into a water or oil bath or water bath. Like in case of the heat treatment operations, generally we do heat treatment operations in the metallurgy, tempering, okay, quenching, okay, annealing, etc. No? Annealing, tempering, quenching, these are all the various heat treatment operations to change the microstructure of the body. So similar things I am proposing here, that a body is heated inside a furnace, heated sufficiently to a high temperature, suddenly taken out of the furnace and exposed to the ambient fluid, maybe atmospheric air, or dropped into some oil bath or a cold fluid bath, cold liquid bath. Because the body is exposed to the hot body, suddenly taken out of the furnace, is exposed to a cooling atmosphere, cooling ambient. The body, the moment it is exposed to the coolant fluid, the body starts losing heat by convection with a convection coefficient of H watt per meter square Kelvin. Okay. So as the time progresses, as the time passes, as the time moves, keeps on changing, the temperature of the body keeps on decreasing. But after a lot of time, sufficient amount of time is allowed to the body, then automatically the body finally reaches the same temperature as that of the ambient atmosphere or ambient fluid to which it is exposed. Okay. I repeat once again the initial statement. A body is kept inside a furnace, heated to a sufficiently high temperature, maybe Ti. Suddenly it is exposed to a fluid, ambient fluid at T infinity. The moment it is exposed, the body keeps on losing heat by convection. What is the mode of heat transfer between the body and the fluid? Convection. Whenever we talk about the convection, it is always notified by what coefficient? Convective heat transfer coefficient H. Okay. The body losing heat by convection to the ambient fluid at T infinity, the moment it is exposed. So the body keeps on losing heat. Because of this heat loss, the temperature of the body keeps on decreasing. That means temperature of the body becomes a function of time. This is the best example to understand the unsteady state. Unsteady state means at different instants of time, you will be observing different temperatures of the body. Okay. Now, I want to establish this function. So, once I establish this function, that is temperature as a function of tau. Tau is the time, a symbol I write. Tau symbol, I use it for the time in second. Tau symbol, I would use it for the time there. Tau symbol. So, as the body keeps on losing heat, the temperature of the body becomes a function of time. Now, I want to establish that function. What is that function? If I can establish that function, from that function, at any instant of time, from the time measured, from the time is always should be measured from any instant. So, what is that instant? When the body is just taken out of the furnace, I put on the stopwatch. Just body is taken out of the furnace, stopwatch is put on. Then what is the stopwatch reading? When the just put on, tau is equal to 0 seconds. When the tau is equal to 0 seconds, the temperature of the body at that instant, which is just taken out of the furnace, is Ti. So, at tau is equal to 0 seconds, the temperature of the body, which is just taken out of the furnace, is Ti. Now, as the stopwatch keeps ticking, time is ticking. As the watch keeps on ticking, the temperature of the body keeps on decreasing. So, I have started measuring the time tau is equal to 0 seconds from that instant when the body is taken out of the furnace. That means Ti is the temperature of the body at that instant when the body is taken out of the furnace, that is tau is equal to 0 seconds. So, from that instant onwards, I keep on measuring the time. So, once I establish that function, at any instant of time, I can get the temperature, or to reach so and so temperature, how much time is taken by the body. So, knowing time, I can get the temperature, and vice versa. Knowing the temperature, I can get the how much time will be taken by the body to reach that particular temperature. So, this is the situation. Body is taken out of the body, first heated inside the furnace to that temperature Ti. For the initial, I means initial. Initial means at that instant of time tau is equal to 0 seconds. That is when the body is just taken out of the furnace. Okay. From that instant onwards, I keep on measuring the time. Okay. So, I am just writing that. Consider a solid body of mass m, volume V, density rho, specific heat Cp, which is at an initial temperature having been heated in a furnace, is suddenly exposed to an ambient fluid, at a temperature of T infinity. Is suddenly exposed to an ambient fluid at a temperature of T infinity. Since the body keeps on losing heat by convection, since the body keeps on losing heat by convection, to the fluid, with a convection heat transfer coefficient of with a convection heat transfer coefficient of H watt per meter square Kelvin, the internal energy of body keeps on decreasing. The internal energy of body keeps on decreasing as the time progresses. The internal is because the body is losing heat from its surface. As a result of this convection heat loss, the internal energy of the body keeps on decreasing. That decrease of internal energy of the body is manifested by decrease of its temperature. The internal energy of the body keeps on decreasing as the time progresses. As the time is passing, the internal energy keeps on decreasing, which is manifested by how it is shown. Manifesting means exhibiting, showing, which is manifested by decrease of its temperature with respect to time. The temperature of the body keeps on decreasing. As a result of that heat loss, the internal energy of the body keeps on decreasing. As a result, the temperature of the body is also keeps on decreasing, because internal energy and temperature are directly proportional. So that now what temperature has become a function of time. Temperature of the body has become a function of time. After a lot of time, after infinite amount of time, finally the body may attain thermal equilibrium with the ambient fluid, same temperature as that of the ambient fluid. Okay. Now I write the initial condition. Let Ti is equal to initial temperature of body at the instant of time tau is equal to 0 seconds, that is when the body is just exposed to ambient fluid. That is when the body is just exposed to ambient fluid. Let T is equal to temperature of body at any instant of time tau seconds later. Let T is the temperature of the body at any instant of time tau seconds later. T is the temperature of the body at any instant of time. T is a function of time. As the time is increasing, temperature is decreasing. I want to establish that function. For that, I would like to write the energy balance for the body at any instant of time. T is equal to tau. Now I want to write the energy balance for the body at any instant of time tau seconds. What is that energy balance? You have to understand like this. The body is losing heat, right? So at any instant of time, the rate of convection heat transfer between the body and the fluid, I repeat once again, at any instant of time tau seconds, the rate of convection heat transfer between the body and the fluid must be equal to the rate of decrease of internal energy of the body with respect to time. Suppose that it is like this. Suppose that at some instant of time tau seconds, the rate of heat transfer between the body and the fluid is say 100 watts. That is 100 joules of heat is lost in 1 second. 100 watts means what? 100 joules of heat is convected from the surface of the body to the fluid in 1 second. That is called 100 watts. 100 joules is lost in 1 second. So the rate of heat transfer, say for example 100 watts. During that 1 second, Because of that 100 joules of heat lost, the internal energy of the body must exactly decrease by 100 joules. I mean to say that the rate of convection heat transfer between the body and the fluid must be equal to the rate of decrease of internal energy of the body with respect to the time. So, for example, after some time, if the rate of heat transfer is 50 watts, that is 50 joules of heat is lost in just 1 second. That means because of that 50 joules of heat lost in 1 second, the internal energy of the body again during that 1 second must exactly decrease by 50 joules. So, at any instant of time, the energy balance says that the rate of convection heat transfer between the body and the fluid must be equal to the rate of decrease of internal energy of the body with respect to the time. So, that is the energy balance. Writing energy balance for the body at any instant of time thou seconds the rate of convection heat transfer between body and fluid should be equal to the rate of decrease of internal energy of body with respect to time. This is a very important energy balance during the unsteady state. The rate of convection heat transfer between the body and fluid should be equal to the rate of decrease of internal energy of body with respect to time. But how do you calculate the convection heat transfer? Whenever you talk about the convection, we always depend upon the Newton's law of cooling. Q is equal to HA delta T. What is that? A is the convection area, contact area. A is the convection area or area of contact between the body and fluid. Wherever the body is in contact with the fluid, that is the area of convection. Okay. HA T minus T infinity. What is the T? T is the temperature of, what is the T there? T is the temperature of body at that instant of time, tau seconds. At that instant of time, tau. Okay. T is the temperature of the body at that instant of time, tau. Okay, A is the convection area. This is the T is the temperature of the body at that instant of time, tau second. That should be equal to the rate of decrease minus mCp dt by d tau. Why I am writing minus? Because as the temperature of the body, as the time progresses, the temperature of the body is decreasing. As the stopwatch keeps on ticking, as the watch keeps on ticking, the temperature of the body keeps on decreasing. That is why this minus sign. That means as the time progresses, temperature is decreasing. Okay, that is why this minus. That that mass could be written, and I could be written as density into volume. Please keep the Cp only in joule per kg Kelvin. This is the energy balance, dt by d tau. Tau symbol for the time, tau symbol for the. So, this minus dt by d tau, you can call it as the rate of cooling of the body in Kelvin per second. per second, how much time is decreasing. We can think of that rate of cooling of the body. In this particular equation, if you watch carefully, many parameters are constant, like density of the body constant, volume of the body constant, specific heat of the body, material constant, A is the surface area of the body constant, H, when you come to the H is the convection heat transfer coefficient, which mainly depends upon the fluid properties. See, H mainly in both forced convection and free convection, H mainly depends upon the fluid. But during that cooling of the body, same fluid is there. Therefore, H value almost remains constant, but if it is a free convection, H depends upon the temperature difference between the body and the fluid. But that is changing. Temperature difference between the body and the fluid keeps changing as the time is progressing. So, as a result, H may change, but that change is very, very little, that too in free convection. If it is a forced convection, H is independent of the temperature difference between the body and the fluid. So, you can forget that. So, that little changes of H that might happen, that too in free convection, can be neglected, and we can treat that H also as a constant, assuming that H is constant during that cooling process. Okay. H is also, if we treat as a constant, now we are left with only two variables. One is time tau and other is the temperature T. You are left with only two variables, time tau and temperature T. All other parameters can be treated as constant. Treating all other parameters constant and separating the variables time and temperature we get HA by rho V Cp. I am separating the variables. D tau is equal to minus dt by T minus T infinity. Temperature on one side, time on the other side. Tau is the time symbol, right? Now we could integrate that. Minus dt by T minus T infinity integral. What limits for integral limits? Tau is equal to, what are the time there? Tau limits. Tau is equal to 0 seconds, correspondingly Ti. Tau is equal to tau, correspondingly temperature. We can take this HA by rho Vcp as a constant, right? We can take it outside the integral. Into tau, because when you write the limits of integration, it becomes a definite integral. Remove this minus and you can interchange the limits. Okay, remove this minus, you can interchange the limits. It becomes log T minus T infinity so it becomes log Ti minus T infinity divided by T minus T infinity. Natural logarithm means is the modular, right? This is the limits were interchanged. The limits were interchanged by removing the minus. So log A by log A minus log B is log A by B. Okay. Now this contains log base E, right? Natural logarithm. Now we could write it as e to the power of HA by rho v Cp into tau is equal to Ti minus T infinity by T minus T infinity. So this is what is the temperature distribution with respect to the temperature variation, and more correctly temperature variation, temperature of the body, how does it vary with respect to the time. Temperature variation with respect to the time is given by this function. From this function, at any instant of time tau seconds, now we are able to calculate the temperature. Knowing the tau, we can get the T, or to reach so and so temperature, how much time is taken, that also can be calculated. So, in knowing tau, we can get the T, knowing T, you can get the tau. All other parameters will be given. A is the convection area, V is the volume. So, from this function, we may notice that in any unsteady state heat conduction, the temperature of the body changes exponentially with respect to the time. So, that at that point you can notice that in any unsteady state heat transfer, unsteady state heat conduction, the temperature of the body changes exponentially with respect to the time, which we can indicate it graphically also. Thus, in any unsteady state heat conduction, the temperature of body changes exponentially with respect to time, as shown in the figure, as shown in the graph, as shown in graph. This is the variation of the temperature of the body with respect to the time. Time tau, this is the temperature of the body. At tau is equal to 0 seconds, at tau is equal to 0 seconds, we have the temperature, no, Ti. But as the time progresses, the curve is asymptotic to the time axis. Curve is asymptotic. Asymptotic means it will not touch at a great distance. Asymptotic to time axis or x axis. Curve is asymptotic to time axis. So, the temperature of the body keeps changing with respect to the time as shown in this graph. And initially, you may notice that initially the slope of dt by d tau is very steep. The slope of the dt by d tau is very high. But after some time, dt by d tau decreases. When the body is almost approaching the temperature of the ambient, the slope is very little. Lot of time is taken, but the drop in temperature is lot of time is taken, but the drop in temperature is very little. Okay. See, that means dt by d tau. What is the dt by d tau minus dt by d tau, which we can call, because it is in the second quadrant, which is the rate of cooling. Rate of cooling of body in Kelvin per second itself is a function of time. It is not only the temperature as a function of time. dt by d tau also, you may notice that dt by d tau also becomes a function of time. This dt by d tau. Why like that? That answer is given in the previous equation. You can look at this. You can look at the previous equation here. This dt by d tau is a function of this temperature difference. Initially, we have a lot of temperature difference between the body and the fluid. Initially, when the body is just exposed to the fluid, there is a big temperature difference, huge temperature difference between the body and the fluid. This is high. Therefore, when this is high, obviously this also will be high. But as the time progressing, as the stopwatch keeps on ticking, this is constant, but this is decreasing. As this is decreasing, this difference keeps on decreasing. As this difference keeps on decreasing, this dt by d tau also keeps on decreasing. When the body is almost approaching the temperature of the ambient, when the body is almost reaching the temperature of the ambient fluid, this is very small. This is almost approaching this. Difference is very small. Therefore, this also will be very small. We can easily notice in that graph. See, this dt by d tau is very small. Is very small because the temperature difference between the body and the fluid is little. Body gets cooled very fast initially, but after some time the rate of cooling decreases. Near the end of cooling, the rate of fall of the temperature will be very small. Okay. Body will not come to the equilibrium so easily. It takes a lot of time to arrive at the thermal equilibrium. But initially, within first 1 or 2 seconds, the temperature of the body drops very, very rapidly. It is not only true during cooling. It is true during the heating also. Suppose that a body is at room temperature is there. Suddenly, it is put in a hot oil bath. It is dropped into hot oil bath. So, supposing there is a hot oil bath is there. Very high temperature oil bath. A body, a finite sized body which is at initial temperature Ta is suddenly dropped into that. What will happen? The temperature of the body keeps increasing, but that increase also will be exponential. Initially, the temperature rise is very fast, very steep. Initially, see this, initially the temperature rise is very steep. After some time, the initial temperature rise that initial temperature is very high. But after some time, the temperature rise is little, decreases. When the body is approaching the temperature of that oil, this dt by d tau is very little. See that? dt by d tau initially very high, after that decreases. When the body is reaching the equilibrium with the hot oil bath, it is very little. dt by d tau is very small. This is here the dt by d tau also function of time, which is a positive here, is also function of time. Tau is the time axis. Okay. So, during cooling and during heating also this rule valid. The rate of cooling or the rate of heating of the body becomes a function of time. Initially, when the body is just exposed to the fluid, it will be very high. But as the time progresses, the dt by d tau keeps on decreasing. Okay, that you can notice that in both cooling operation and as well as the heating operation. So, that is another thing. One more thing we may notice here is, this has got the units of second. Therefore, HA by rho VCP should have the units of per second. Is it not? It should have the units of per second. If you reverse it, rho VCP by HA should have the units of second. Therefore, that term is called as the time constant of the body. Since rho VCP by HA has got the units of second, It is called time constant of body. It is called time constant because it has got the units of second. What do this time constant of body signify? What does it mean? What does it signify? It signifies how much time the body may relatively take in approaching the temperature of the ambient. Need not reach. So, time constant more mean high time constant, long time constant means the body takes a lot of time in approaching the temperature of the ambient or in reaching the temperature of the ambient, in becoming closer to the temperature of the ambient fluid, okay, to which it is exposed. Supposing if the time constant is little, the body very quickly approaches the temperature of the ambient fluid. So, it indicates the generally relatively how much time the body may be taking in approaching the temperature of the ambient fluid to which it is exposed. Time constant, I am writing the significance. Time constant of body signifies how much time the body may take relatively, how much time the body may take relatively means more or less, how much time the body may take relatively to approach the temperature of ambient fluid to which it is exposed. Time constant of body signifies how much time the body may take relatively to approach the temperature of the ambient to which it is exposed. For thermocouple, it is very small. A thermocouple is a very small bead. For thermocouple, while measuring the temperature of gases, flowing in a duct, while measuring the temperature of gases flowing in a duct, it is very small. It is very small. It may be in few seconds, fraction of a second or 1 second, maybe 1 or 2 seconds. Maybe 1 or 2 seconds. Thermocouple is a tiny bead, very small bead, a tiny bead, a small bead placed. No, this is a thermocouple bead. I am just giving the example of this time constant. Thermocouple bead usually measures the temperatures of the hot gases flowing in a duct. It can measure up to 1000 degrees Celsius also. So, this is the bead. For this thermocouple bead, this time constant will be very small because size is very small. Look at this, V by A indicates the size, the relative size of the bead. It will be very tiny bead, which is a tiny, thermocouple is a tiny bead, small bead, tiny spherical bead. It is very small, okay. So, you understood the significance of the time. If the time constant is more, the body may take a relatively a longer time in approaching the temperature of the ambient fluid. For example, for ordinary thermometer, generally when we get the fever, thermometer is kept in the mouth. For there, the time constant may be around nearer to the 45 seconds or 50 seconds or maybe sometimes 1 minute to record the temperature of the body. While when you are having fever, you will be putting the thermometer to measure the temperature of the body. There it may be around 45 to 45 seconds to the nearing to the 60 seconds. That is the time constant of that thermometer. Okay. Now, in the all this entire analysis which I have done until now, there is one hidden assumption, underlying assumption that the temperature of the body is uniform throughout its mass at any instant of time. In the entire analysis, whatever you have spoken, there is one hidden and underlying assumption that the temperature of the body throughout its mass is uniform. Uniform means same at every location within the body at any instant of time. No doubt the temperature of the body is decreasing with time. But if you just consider the body at any particular instant of time, the temperature of the body throughout its mass is uniform or same at every location. That is called as the such kind of an analysis. Very important name here, it is called lumped heat capacity analysis. Very commonly asked question in GATE. This question was asked so many number of times. Lumped heat analysis means there are no internal temperature gradients within the body. There is one important criteria when you can apply this lumped heat analysis. Means there is one important criteria in the form of the Biot number, which is a dimensionless number. Now I am giving that important note. In the entire above analysis, it is assumed that the temperature of body is uniform throughout its mass at any instant of time. The temperature of the body is uniform throughout its mass at any instant of time. That is, temperature is only a function of time, but temperature is not a function of space or location. Different locations having the same temperature. It is not a function of space or location within body. Throughout the body, we are observing the same temperature. Such analysis is known as lumped heat analysis, or sometimes it is called lumped heat capacity analysis. This name is very famous. In this particular conduction chapter, lumped heat analysis means temperature is only a function of time. That is in this analysis, there are no internal temperature gradients. There are no internal temperature gradients within the body. There are no internal temperature gradients within the body. No temperature gradients. Temperature, that means if this is the body, at any instant of time, if you take any two locations within the body, suppose if you take periphery temperature, core temperature, the periphery temperature and periphery and core, if you just take the temperature difference, this temperature difference almost approaches 0 at any instant of time. This temperature difference between the core of the body, and the surface of the body, this temperature difference almost approaches 0. That kind of an analysis is called all locations are having the same temperature at any instant of time. No internal temperature gradient. Such analysis is called lumped heat capacity analysis. Very, very important term here. There is one important criteria for lump. When you can write this lumped heat analysis, criteria for lumped heat analysis, there is one important, when you can apply, that means there is one important criteria in terms of the dimensionless number. Biot number should be less than 0.1. First dimensionless number I am writing. In heat transfer, we come across so many dimensionless numbers in future: Nusselt number, Reynolds number, Prandtl number, Grashof number, etc., Stanton number. So many numbers we come across. But this is the first number in conduction, conduction we usually come across less numbers only here. First number which I am introducing is the Biot number. Biot number is a dimensionless number named after the Biot, a person, okay, where Biot number is given by, this is the formula for the Biot number. Hs by K of the solid. S is the characteristic dimension meant for calculating the Biot number. Characteristic dimension of body which is used to calculate the Biot number value of the body. Characteristic dimension of body. Biot number is not a property of the material. Okay, it is a dimensionless number. S means the characteristic dimension of the body which is used to calculate the Biot number. It is given as volume divided by area. Volume of body divided by area. For a spherical body, for spherical ball, S is equal to volume by area, surface area is equal to 4/3 pi r cube. What is the area, surface area? It is 4 pi r square. It will become r by 3 for S, you know. But as long as this Biot number, that is Hs by K, is less than 0.1, yes, lumped heat analysis, temperature is only a function of time only. Temperature not a function of location or space. Throughout the body we see the same internal temperature gradients, we can be neglected. There may be little gradients, small gradients, but that can be neglected. Negligible internal temperature gradients as long as the Biot number is less than 0.1. I can give the definition of Biot number also. Definition of Biot number also we could write like this. Biot number you could write this as S by Ka divided by 1 upon Ha. Okay, what is that S by Ka? It looks like B by Ka, B upon K. It is the conduction thermal resistance. This is the convection thermal resistance. So, this is the internal conduction resistance offered by the body, internal conduction resistance offered by the body against the internal conduction heat transfer divided by the surface convective resistance at the surface of the body, between the surface of the body and the ambient fluid. It can be written as internal conductive resistance offered by body divided by external convective resistance. ICR by ECR. See, when the body, it is like this, you can understand this Biot number like this. See, in this particular unsteady state heat transfer, there are two different modes of heat transfer happening simultaneously. See, from the surface, it is convection to fluid happening, convection heat transfer to fluid happening. That means the surface of the body temperature decreasing. Immediately body responds because the temperature of the convection, by temperature of the periphery it is decreasing because of this heat loss. Immediately body responds by supplying the heat by conduction. What happens internally within the body is conduction. What happens at the periphery is convection. There are two different modes of heat transfer happening simultaneously during this unsteady state heat transfer. As compared to this, if it happens very fast, yes, this lumped heat analysis is valid. Why it is happening very fast? Because the conductivity of the, when the Biot number will be low, when the Biot number is low, conductivity of the body is high, like a copper ball. Like a copper ball, supposing if the surface is getting cooled, immediately body supplies the heat from the core of the body to the periphery, because the conductivity could happen, conduction could happen very rapidly, because the thermal conductivity of the body is high. When the K is high, Biot number will be low. Okay, when is the Biot number will be low? When the K is high, or if the size is low. Size S you can refer to the size. Actually, it is not meaning that. S is a characteristic dimension. If the size of the body is small and if the conductivity of the body is high, automatically lumped heat analysis is valid. That point we can see, because this conduction happens very rapidly and as compared to the slow convection heat transfer happening at the periphery. That means if the Biot number is low, that is if during the lumped heat analysis, the convection heat transfer happening at the periphery may be occurring slowly, but this conduction heat transfer happens very fast, very quickly in all the directions. Okay, so because the conductivity of the body is high and the size of the body is a little small in size, slender sized body, small sized body, therefore the internal temperature gradients can be negligibly small. That is the main concept of lumped heat analysis. Okay. Biot number will be automatically less than 0.1 for small sized bodies like small spheres, thin plates, slender rods. Slender means thin rods, slender or thin rods, made up of good thermal conducting material, made up of good thermal conducting material like copper, made up of good thermal conductivity material, high thermal conductivity material like copper, aluminum, etc. A body is made up of a good conducting material relatively smaller size. Byte number will be automatically less than 0.1. We don't have to calculate the byte number also. That means throughout the body you will observe the same temperature at any instant of time. That is the main importance of this lumped heat analysis. In case if byte number if the byte number is greater than 0.1, then lumped heat analysis is not valid. Then how to get the temperature? Then to get the temperature, at any particular location, and at any given instant of time, Haisler charts must be used. You have to use the Haisler charts. In these Haisler charts, we see two different dimensionless numbers. We observe two different dimensionless numbers . Two different dimensionless numbers. They are number one, byte number, which you already seen, that is Hs by K. Number two, Fourier number, that is alpha T by S square. S is the different for different shapes of the bodies. Fourier number, FO, it is called Fourier number. This is the byte number. Tau is the time. S is the characteristic dimension. And tau is the time. Fourier number is also called as the Fourier number. It is also known as the dimensionless time. It is also known as dimensionless time. The other name of the Fourier number is dimensionless time. So in the Haisler charts, in these Haisler, when we have to use these Haisler charts? When do we need to use the Haisler charts? When the lumped heat capacity analysis is not valid. Haisler charts are required to be used only when the lumped heat capacity analysis is not valid, that is when the byte number value goes above 0.1, okay. Otherwise, if the byte number value is less than 0.1, yes, we can always make use of the lumped heat capacity analysis, okay. Generally, lumped heat analysis will be valid for all the small sized thin plates, slender rods, small sized spheres need not be very small. Sphere need not be very small. Supposing if you take around 5 centimeter diameter ball, spherical ball made up of a copper exposed to the air, yes, still lumped heat capacity analysis is valid. 5 centimeter it may not be too small, thin body, okay, too small sized body, but still because it is made up of the copper material, though body is little bit bigger, though K is, because since the K is very high, still the Biot number falls less than 0.1. Biot number is HS by K. Though size is little bigger, S is little bigger, K, if the K is too big, like that of a copper or aluminum, though body is little bit bigger, still the lumped heat capacity analysis is valid because Biot number value becomes less than 0.1. So, as long as, please remember that lumped heat analysis is valid as long as the Biot number is less than 0.1, where S is given by HS by, Biot number formula is HS by K, S is given by V by A. For spherical body it is R by 3. Okay. If in case if the Biot number value goes above 0.1, we need to make use of the Hassler charts. Okay.